I'm going to move my workspace up here so that we can save room. We still have this situation, volumes are constant, everything else, but now I want to look at this stoichiometry in the longer way, right? So what do we need, have we said in the past, to do stoichiometry? We need moles, and we said it, well, we said right there, N would be PV over RT, and so we can do that. N would be PV over RT. And in this case, your pressure for the hydrogen is 3.00 atmospheres. Our volume is 2.00 liters. R is 0.08206 liter atmospheres over moles Kelvin. And T is 298 Kelvin. Don't forget we have to turn Celsius into Kelvin to make that work. This ends up being 0.245 moles of hydrogen. All right. Similarly, for our, and I guess I'm just going to change the colors here so it's visually a little better. For our moles of oxygen, and this time there's 4.00 atmospheres from right there. Still 2.00 liters, still 0.08206 liter atmospheres over moles Kelvin, and still 298 Kelvin. So hopefully what you notice here is the 2, R, and 298 are the same for both, and that relates back to why we can just do the stoichiometry with pressures. In this particular case, you end up with 0.327 moles of oxygen gas. This is what we have, and we're going to use it to find out what we need. From my balanced chemical equation, it tells me for every 2 moles of hydrogen, and this time I am using moles, 2 moles of hydrogen, there's 1 mole of oxygen. All right, so we end up with 0.1225 moles of oxygen that we need, and 0.654 moles of hydrogen. Something of note, we have 0.2 and we need 0.6. We don't have enough. That hydrogen is our limiting reactant, which was true before as well, and it should be. We have 0.3, we need 0.1. We have more than we need, so that becomes our excess reactant. So we're starting to see where our answers lined up here. We're going to do this same calculation for amount excess, where we'll take what we have, in this particular case 0.327 moles of oxygen, and we're going to subtract what we needed, which is 0.1225 moles. And we end up with, in that particular case, 0.2045 moles of oxygen as our excess. All right? So it's not the answer to our question, but it's an answer we are going to use to get there. Our theoretical yield we'll calculate the same way we did up here, comparing our limiting reactant to our product. In this particular case, we had 0.245 moles of hydrogen, and we know for every 2 moles of hydrogen, there's 2 moles of water. And so 0.245 moles of water. And that is our theoretical yield. Now, we have an excess in moles, we have a theoretical yield in moles, but we want to get a total pressure. The same thing we had written here is still true, and that is that the total pressure is going to be the sum of the partial pressures. Partial pressure of A plus partial pressure of B. In this case, that's the partial pressure, again, of our excess, and the partial pressure of our product. And we're going to need to turn these mole numbers into those. So I'm going to say like the partial pressure of the oxygen excess plus the partial pressure of the water. So what's in that final container? In the final container, you have used up all of the hydrogen gas. It was your limiting reactant. You have some oxygen left over, and you've made some water. And so the pressure in the container is going to be based on the amount of oxygen we have left over and the amount of water we made. The catch is these are moles, so we'll have to do some quick converting there. Again, we know PV equals nRT, and I'm going to sneak that over here, I guess. PV equals nRT. And to get the to get the pressure then, it's nRT over V. And we have these mole numbers here. Our partial pressure of the oxygen is going to be our moles of oxygen, 0.2045 moles, R 0.08206 liter atmospheres over moles Kelvin, times T, which is 298, and we're dividing by our volume, which is 2.00 liters. And I do want to point out, over here we had moles plugging in pressure, and here we have pressure plugging in moles. We're just coming full circle and undoing what we did originally, and that's why things end up like they do. So the pressure of the oxygen is going to be 2.49 atmospheres, which is probably 2.50 with rounding. And then, just to stay with our color scheme here, our partial pressure of the water is going to be our moles of water, which is 0.245. We've still got our 0.08206 liter atmospheres over moles Kelvin, and we still have 298 Kelvin. In the bottom we still have 2.00 liters. And again, the fact that we multiplied by 2 and now we're dividing by 2, we divided by the ideal gas constant R, we're multiplying by the ideal gas constant R. We divided by temperature, we're multiplying by temperature. We're just undoing everything we did there, which means we probably didn't have to do it in the first place. In this particular case, that's 3.00 atmospheres as the partial pressure of our water, our theoretical yield as a partial pressure. So let's get our final answer right here. This is our 2.49 plus 3.00, which is 5.50 atmospheres for the total pressure. And you may notice those two end up the same. And I realize there was some slight hand waving going on, 2.49 to 5.50, but it is the same. So let's highlight that. And again, that was the long way. You don't necessarily have to do it that way. And just to do my due diligence here, we had for our oxygen yellow, and for the water we had blue, all right. There's one other thing I'll mention. This is just kind of a side note, but this is kind of important, working backwards on Dalton's law of partial pressures, and that is we didn't need to take 0.2045 and 0.245 and calculate them separately. And I'm guessing somebody's pedantic alarm was going off when I did this. We didn't actually need to do this. We could have just said that P total would be N total RT over V, where N total is your total moles. And we can add that up, 0.2045 plus 0.245, so we can add this up. And we end up with 0.450, it's actually 0.4495 moles, and I'm just going to call that 0.450. So we have then 0.450, 0.08206 liter atmospheres over moles Kelvin, and 298 Kelvin. Did we squeeze that on the screen? Yep. And we're dividing by 2 liters, and we do end up with our pressure total as 5.50 atmospheres again. All right, we'll hit that with our orange highlighter. And those are all or scenarios. You don't have to do all three, obviously, because all three of them get you the same answer. But if you look here, multiply by r, multiply by t, divide by v, do the same thing. You can simplify that by adding these and then multiplying by that like quantity. So there are some shortcuts you can use when you're doing gas stoichiometry. It doesn't just have to be moles. You can do pressures or even volumes when you have other things constant.